this guy up. So yesterday we were talking about some of these basic series parallel circuits that we've been using, and we were Thevenizing these guys with the idea that we're going to use these two different loads, a 6.7 meg and a 5.2 meg. So yesterday we started off and we had found our V-Thevenin. So V-Thevenin is the voltage across AB, which in this case it's the voltage drop just across R2. So we take the 1.2 meg divided by the 1.2 meg times the 5 meg, multiply that by 145, and that gave us 28.065 volts. So that is our Thevenin voltage to start with. Yes. Well, and in this case, this voltage that we found is not the actual one. This is our Thevenin voltage. So not the actual voltage yet. So remember, the first step we had is we have a resistor here. First step is we take out the load, and then we find V-Thevenin and R-Thevenin. So to find V-Thevenin, we have to find the voltage between these 2 points. And in this case, it's just this voltage that we're going to calculate across R2. But don't get it confused. This isn't the actual voltage across R2. This is just our, yes. So just our Thevenin voltage. And then we find that we just used voltage divider, which is the voltage total multiplied by the resistor we're looking for over the resistor total. Okay, so now that we do that, now that we've found that part, we need to find our R-Thevenin. So for finding R-Thevenin, the rules are to short the load, and then what resistance would we be seeing from those 2 points? So if we were to hook an ohm meter across those points, what would we see? So first step, we short the load. So that removes that completely from the circuit. This R1 we could bring across and bring down. So what we're going to see from looking back from point A and B, we're going to see R2 in parallel with R1. That's going to be our R-Thevenin. Now again, we can use either of the methods that we have, the reciprocal method or the product over the sum, to find this value. Either way, we should get the same answer. I prefer using the product over the sum. So we'll take the 1.2 meg multiplied by the 5 meg, and we're going to divide that by those two added together. So in this process, we're going to end up getting 967.742 kilo ohms. Everybody good with that value? Okay. So now we have the 2 values we need to plug into our Thevenin value. So the hard part really of this circuit is over, because now we could swap loads out left and right, and it's not going to matter what we do, because we found R-Thevenin, V-Thevenin. It doesn't take those into account at all. So now, when we were done, we want to come back and find these voltages. So we come back to our Thevenin equivalent circuit. Put in V-Thevenin here. We have R-Thevenin here. So we've got 967.742 kilo ohms. We have our load, and we have our voltage, 28.065 volts. So now the thing that it's asking for again is we have a 6.7 and a 5.2. So while we're here, we might as well find both of those to go and then go back and calculate. So we need to find the voltage across R3 at, what did I say, 5.6? 6.7 meg and 5.2 meg. So the voltage of R3 at our 6.7 meg. So we plugged that value for this resistor in, and now we're going to solve and find out how much of this Thevenin voltage is going to drop across this load. So again, we're just going to use voltage divider. So we take 6.7 meg over 6.7 meg plus R Thevenin. And I'm just doing that because that's just a lot of numbers to write. So what should we expect to see? Just rough numbers looking at how these guys are comparing. We have about a meg resistance here. We've got 6.7 megs resistance here. So what should we be seeing? Yeah, we should see, and not just more, we should see most of it. So yeah, 5/6 of the voltage at least, probably a little bit more. But so we should know, we should be seeing 22-ish volts, 23 volts, something like that. So while we're doing these calculations, think about what should I be seeing, and what's these ratios. Most of the voltage is going to drop here. So we take that and multiply that by our V Thevenin. And what do we get for the voltage drop across R3? Okay, does that match? So we've got that voltage. How much current do we have flowing through this? How much? 3.66 microamps. Okay? Any issues with that? So while we're here, let's also solve for our voltage and our current at the other load. That way we can go back through and we can calculate kind of all of them at once. So now we're going to do the same thing, but instead of a 6.7, we're going to drop in a 5.2. What should we expect to see with this voltage? What? You're going to drop a little bit less because we have less resistance. So what does that voltage come out to be? How much? Okay. And then the current, we take that voltage divided by its resistance. What kind of current do we get? Okay.
Well, that's how I could do just because it's kilograms, right?
Yeah, so yeah, because these are in meg, those are in kilo. So those ones you want to shift it down 3 decimal places.
Okay.
So well, your 9, so your 9.9 or your 967 is supposed to be 0.967. Because if you're just gonna do those numbers, you have to make sure you have them in the right units. Yep. So you either have to put the units in for everything, or make sure as you're treating them the same. That's how I do a lot of my calculations. Is I'll just drop off, like if I'm dealing with meg, anything in K is then decimal points of a meg. So I automatically rotate those through, so I can kind of keep them as whole numbers when I'm running them through my calculator. The voltage of R3 divided by R3. So that one you have to put in the meg. All right. So we end up with these two values. Okay, I'm just writing them off to the side so we can come back up. So now that we have solved those values, now we're going to put that load back into the circuit, and we're going to solve the circuit based on those values. Nope. The only thing that we have solved for is the voltages, or the voltage across R3 and the current through R3. Yeah, for those two resistances. Now we got to go back through and we got to calculate what VR1 and VR2 is at the two different points. So we put our resistor back in, and we're going to look at the 6.7 first. So with that, we have 24.52 volts across R3 with this much current. How much voltage do we have across R2? 24.5 volts. So VR2 is 24.55 volts. If we have 24.55 volts across this parallel network, and we started with 145 volts, how much voltage do we have across R1? Yep, 120.48. So then we're going to come back and look at this guy. Now we're going to look at the 5.2 meg. So across R3, we have the 23.661 volts. What's our R2 value? 23.661. Why? They're in parallel. Obviously, those don't equal. I'm just putting them on the same line. Okay, VR1, if we've got 23.661, how much do we have dropping across R1? And just like that, we can solve these voltages. What if we put in another one, and let's say it was 1.2 meg? Do what? So how far back do we have to go to if let's say you solve this based on these two guys, and then your manager comes back and says, "Oh, hey, by the way, we need you to run the calculations on this part as well." Go back to the Thevenin equivalent. So we come back down here, and we look at it at the 1.2 meg. Yep, we just do the voltage divider again. We don't have to recalculate any of that. So then we can simply say we have 1.2 meg divided by the 1.2 meg plus the R Thevenin value multiplied by the 28.065. What do you think is going to happen with this voltage? It's going to go way down. What would we be looking about? With the 1.2? A fifth of it? How much resistance do we have here? Almost a meg. They'll be about the same. So we should see about half of this would be 14, but I'm guessing it's going to be comparatively, we're going to see about 16. So does that come to be? So that's what I was saying, is use your guesstimates. You guys have a good enough understanding of what is going on that when you're just getting these values, do they actually make sense? Should I be getting that? So looking back at this guy, you can think, okay, I've got almost a meg here. I'm shooting at just a little over a meg. They should be fairly even, and they should split this value pretty close to in half. This side obviously is going to have a little bit more because this is more than a meg and the other one's less than a meg. So we should see that difference. But ballpark, I knew we should be right around 15, 16 volts. That's one skill that it does take some time to learn, but if you can kind of get to where you can kind of guesstimate where they should be before you plug them into your calculator, that's when you know you have an understanding of a full understanding of how these circuits work, is if you can start to see some of those relationships. It does take a while. I don't expect you guys to be able to do this overnight, but start be thinking about that when you're solving these. Do my answers actually make sense, or are they just answers? I know it's kind of hard to do that when you're in the thick of things, right in the middle of it, especially when you're under a time crunch, but that'll help save you a lot of time. Is while you're looking at this, you're like, oh, wait a minute, my number came up, instead of like 15, it came up as 0.015. I probably put in the wrong prefix on one of these guys. Because I know I do that a lot. I'll punch in the wrong one for milli and micro all the time. And it's like, well, does this answer make sense? Not really. Why not? Type of a thing. Okay, so we got the 15.536 volts. So if we come back up here, again, how much voltage do we have R2? 15.536. How much do we have across R1? And that could be something that your boss says, hey, I want this changed. And if you have your notes with you, if you have your lab book with you that you're doing all this stuff in, you could flip back to that page and you could actually just crank out this number for them right then and there and give them an answer. Sometimes that's great. Other times it's best, take it back, make sure you get your information correctly before just spouting off an answer, and then, submit it to them. A lot of times it comes down to they'll ask you this over email. You'll reply an email. That way you got traces that you're doing your job. They're asking questions, things like that. One thing that you guys will find is documentation is key. I know you guys hate it now with your lab books and how I'm making you write down every little thing. But when you get into industry, your lab book will actually save you your job sometimes. If you can go back and prove that you worked on this tool and you fixed this problem, or you brought this problem up and didn't get addressed, that can be the difference between you getting fired and not. There was times where we had some tool failures, and they're like, well, we just had this tool failure. Somebody went in and fixed it. Well, their fix didn't hold. Or maybe it wasn't quite the right part that burned something out. But there's at least documentation saying that, hey, people are trying to fix this problem. This problem goes deeper than what we were expecting. Plus, when you have tool logs and things like that, you can look back in the history and see, does this tool have this pattern of this part wearing out? If so, how long does it last? And that's the other thing you can do, is you can start getting schedules set up. So if you have a tool that let's say every 6 months it burns up a bearing, you could put that on a schedule. So when it goes down between 4 and 5, or between 5 and 6 months of service, you take that tool down, you pull that bearing, and it's going to take you a little bit of time to do it. But it's usually easier to pull a bearing before it fails than after it fails. They usually seize, they get stuck, they don't come out very easy. So you can start tracking these, just not even with electronics problems, but with problems in industry. You're going to see all these things, and that's why the documentation is so important. Plus, then you can have these answers. So maybe you have this solved, and then 2 months later, your boss says, well, what if we were to change it to another part? Instead of having to spend the time to go through the whole thing, you can flip back to those pages and go from there. It'll save you a lot of time, and also in the future. Okay, any questions with those guys? Swapping those in and out for the load. And going back through and using that information to solve the rest of these circuits. Does everybody kind of have an idea of how these are stepping through all these? Like I said, they will take practice. Take the quizzes. That's what they're there for, is for practice. If you have questions, email me, call me, text me. The biggest thing is if you do call for help, send me a picture of your work with it. That way, just to take a screenshot of the page you're working on. That helps me identify the problems a lot faster. If I don't see any work, it's kind of hard for me to pinpoint where you got off. At that point, it's just me guessing. Okay. Thevenin, like I said, is a very useful tool. For these simple circuits, it's not necessary to use Thevenin because we have other means. But we're going to start talking about a different kind of circuit. So we're going to get into the bridge. We got R1 and R2, R3, R4, and R5. Kind of naming them in this convention, going around clockwise. So part of the things that we're going to do in this for these quizzes is we have a couple of them for bridges. We're trying to find our VR3 analysis. Then we're also trying to find the voltage of all of these guys. So one thing too is this circuit is the exact same as this circuit. Yes. So if you have a circuit like this, you can change it how it looks as long as you maintain the connections. So if you look, we got 1, 2, 3, 4, and 5. What is resistor 1 connected to? Yep, 1, 2, 3, 5, and the power supply, the positive end of the power supply. So we look, do we have those same connections? R1 is connected to the positive of the power supply, it's connected to R2, and then it's also connected to 3 and 5 together. So all we've done is we've taken that point and spread it open. Made it a little bit easier, a lot of it easier to look at and to solve. But they're still going to behave the exact same way. Okay. So when we do this, we're going to follow the exact same steps as before. So we have a 3.6K ohm on R1. Oops. R2 is a 2.2K ohm. R3 is a 5.1K. R4 is a 3.3K. And R5 is a 2.2 kilo ohm. And we have 64 volts. So what I want to know is I want to know the voltage across R3. Now, when we're reading these things, it's important to know how are we measuring it. So in this case, I want to measure the voltage in this polarity. So I'm putting the positive of my voltmeter on this side, and I'm putting the negative on this side. That's going to be important for how we're measuring these. On the quiz, it'll tell you how it wants it measured. I think most of them go across this way. Generally, we're going to measure left to right, top to bottom, unless we have a ground. So, what I want to know in this circuit, I want to find our R Thevenin, the V Thevenin, and simply the voltage across R3. We will get to the point where we will solve for all the voltages of this guy. And this is one of the things we'll talk about at the end of the circuit. So again, we're going to use Thevenin. So what are the rules of Thevenin? Take out the resistor that we're looking for. So in this case, we're going to remove R3. And then we're going to solve for our V Thevenin and our R Thevenin. Now, one of the cool things about this is we have to look and we have to analyze the circuit. How are we going to find what that voltage between A and B is? What tool do we have in our tool belt to solve for this? If we want to go from one point to another. Kirchhoff's voltage law. So if we start at point A, we want to get to point B, all the voltage drops from those 2 points have to equal what? 0. Everything has to even out. So we start at point A and we go around. Well, we come here, which direction do we go? Doesn't matter. It'll work either way. Okay, what's the polarity of these resistors when they're hooked up like this? Positive to negative from the top. Because this is where our battery is, it's going to charge positive over to here. This is going to have less potential. This is going to be a positive, this is going to be a negative. Same with this guy. So as we come around, we go up, we go down, it does not matter. So this way we come up, we're going to have the negative voltage drop across R1. We come around the circle. We have, what do we run into next? A positive R2. We come down this direction and we come here. What do we have to have across this meter to get it equaled out? Has to be equal to 0. I'll put that in parentheses because it could be positive or negative. We don't know. So just like what we were doing with currents, we can do it with voltages. They have to equal out. So how do we find what these voltages are for this? Just voltage divider. Yeah. Well, they're not in series because you got to look at how they are in the total circuit. So each individual branch, so R1 we could find using voltage divider because what's in its series branch? R1 and R5. Because there's nothing connected here right now. So these two resistors are in parallel with our supply. So if those guys are in parallel supply with nothing else in here, it's just going to be the voltage divider between these two components. Same with over here. We have R2 and R4 are in parallel. So the combined voltage between R2 and R4 is 64 volts. The combined voltage of R1 and R5 is 64 volts. The same thing would happen if we went down this direction. Only in this way we would add VR5, we would subtract R4, and then whatever's left is what our answer has to be. So solving for VR1, $39.746. Okay, and how did you get that? We're going to get a workout on voltage divider. This is one of the biggest formulas we use next to Ohm's law. Until we hit AC. Okay, is that the same value we're getting? Okay. So we have a 39.724 volts across this guy. So let's plug that into our equation here. So we have a negative 39.724. So now let's find the voltage drop across R2. Okay, and how did you get that? Okay. Okay. That's using your clues that you have in your circuit. It saves you from having to do a lot of excess calculations. These two happen to be equal. So the 64 volts, you're going to get dropped across here. Well, what about this guy? Is that going to give you the same one, though? No, that's the difference. If these two were exactly the same, then yes, you could do that. But you have to look at just because they're the same resistance, they have just a slightly different balance. So but still, yeah, your answer is going to be close. So what would you expect it to be? With this being 3.6, so you'd have how much left over? You said the 25.142. Okay. With this one, we have more or less resistance total. A little bit less, so that's going to have a little bit more of a share. We lost it off of this guy. So what we should see is a value slightly higher than that when we actually look at this guy. But that was a good way to infer from that. So we're going to find it the same way. So 2.2K divided by the 2.2K plus the 3.3K, multiplied it by the 64, and that gives us 25.6. Yes. So AB. So we are measuring it in this way. Okay. So now that we have this, we have to solve for our AB voltage. So we have, I'll write this a little bit bigger. So we have negative 39.724 plus 25.6. Oops, I wrote 1.6 again. Plus some value of AB has to equal 0. So now we just solve for this unknown value. So we take the negative 39.274, we add the 25.6, and that gives us what, Max? 124 equal to a negative VAB. Yep, and we want to get rid of that negative sign because we still haven't simplified it. So we divide both sides by -1. That turns both of these guys positive. And we end up with VAB is a positive 14.124 volts. When we come back and look, we're going to have a positive and a negative 14.124 volts because we're measuring in that direction. Because we have our positive of our meter here, the negative of our meter here, we have to have a positive voltage. Yeah. It would change the polarity of the actual of how it would come in. So this would switch because now we would have a negative and a positive on our meter, which can happen. That's just Thevenin. Okay. But again, this is one where you solve it once, then you can go in and we can change this load as much as we want, and it's not going to cause us that much more work. Because that's just how I went. Yeah. If we took it down this direction, up and around, down into here, we could do that. One continuous loop without crossing ourselves or crossing the line that we've already done. So let's look at that, because that is a good question. Okay? So we'll start from here, and let's go this direction. So we'll go this way, up, around, down, and back to here. Okay? Just for kicks and giggles. What's the first thing we run into here? Positive VR5. What do we run into next? Negative 64. What do we run into next? Positive R2. And then plus some value for VAB has to equal 0. So what's the value for R5? Okay, minus 64. VR2 we already found. $24.275. I got 24.276. Is that where you're getting now, or? Said I want to make sure we get on the same page. Okay, so we'll put in 24.276. VR2, which was 25.6, plus some value of VAB equals 0. So we've got 24.276, we minus 64, we add 25.6, and we end up with so no matter what direction we go, we will get the same answer. As long as you remember that you can't cross. So the other thing is we couldn't come up here, come down this guy, because now we're back at point A. And that's not what we want to get to. We want to get to point B so we can find this value. Make sense? It is, like I said, it is a roundabout way to do it, but you can do it that direction if you so choose. All right. So we have our voltage. This is our V Thevenin. So now, what's the next step? What do we have to do? Short the supply and find the resistance from point A to point B that would be measured. So, I'll redraw the circuit. Our supply is shorted. We have from point A to point B, and we want to measure as if we were coming across there with our meter. We've got R1, R2, R4, R5. Okay? Let's redraw this so it makes more sense. Okay? So we're going to start at point A because that's where we want to go. What is point A connected to? R1 and R5 in parallel because there's multiple current paths. So we have R1, we have R5. What is the end of R1 connected to? R2 and back around to R5 and R4. So then they would be in series with each other. So when you're looking at these guys, physically go through and redraw how they're connected. So in this case, we've got R1 is connected to R5, R2, and R4. And R4 is connected to everything else. So now when we get this, our R Thevenin is our RAB is equal to R1 in parallel with R5. That's in series with R2 in parallel with R4. So we got 3.6K, 2.2K, 3.3K, and 2.2K. So R1 and R5 in parallel, we got 3.6K times 2.2K over 3.6K plus 2.2K. That's this value. We have 2.2K times, or 3.3K over the 2.2K plus 3.3K. That gives us that equivalent. Yep. And then we're going to add those guys together. 2.685. Okay? Because I would expect that this value here is going to be slightly less than 2.2K. Well, not slightly. It's probably going to be around 1.2 because it's about a third, about half in there. This one's going to be just slightly around, or I guess slightly around that same area. So if you take half of the 1.2 or 2.2, add them together, you're going to get back up to about your 2.2. So guesstimation wise, yes, that's in the ballpark. Do we agree with that value? Okay, so we'll come back here and we'll just walk through it again. So we're looking at point A. We're going to start there. Yep. Well, the problem is that because they're all connected together. So if you wanted them as series, like this, okay, except for you also have R1 is connected to R5. So on our redraw, we have to have that there. So then this just becomes a mess. And so the idea here is we still want to have one connection just to reduce the number of contact points with keeping everything together. This is one that you just kind of will have to see that if you get those and you have a line like that in between them, you can flip that a little bit and know that those guys are in series, those guys are in parallel. Because we still are maintaining all the connections. Because you got to remember, a piece of wire has 0 ohms of resistance, and that's essentially what we've done, is we've connected everything to each other with as minimal connections as possible. That's the other thing. Because the other one we had, I think, what was it? 1, 2, 6 connections, and this one gives us 5 nodes or something like that. Plus, find the way that makes it look easier to you. Because the other thing you're looking at too, how is R1 and R2 and R4 connected? Are they connected on both sides of each of the resistors? Or are they only connected on one? So looking at R1 and R5, we know those guys are in parallel, right? Because we're connected around. How is R1 connected to R4? How many connections does it have? Just one. So we have R1 is only connected, it's only connected to R4 through this. So if there's only one connection between R1 to R4, what does that mean? Those are in series. You can't, because you run into R2. You can't directly connect to another component through another component. That's why we have the series with those guys, because there's only one connection from R1 to R2. There's only one connection from R1 to R4. And same with the other one. There's only one connection from R5 to R4, and there's only one connection from R5 to R2. They have two connections to each other. Right. And that's why I was drawing this guy, to show how everything's connected. That's what I'm saying. These ones are difficult for that fact, is we're using all the different tools that we have. We're using Kirchhoff's law. We're using our parallel laws. How many current paths do we have from one point to the other? That's what determines what's in series, what's in parallel. It takes some time. But this is the big key here, is being able to redraw your circuits like this. Make sure you have all the connections between each component. And that's why I started with here. We went with A. What's A connected to? Okay. Well, what's R1 connected to? What's R5 connected to? And in this case, we know that there's only one connection, so we only have one connection. It will, unfortunately, it will. But one of the things too is like, okay, I can kind of start to see that. I have an understanding of the idea behind it. I may not quite fully grasp it, but if you take it and kind of move forward, it will slowly start to become clear. Some things you have to kind of take and accept in electronics until you get into later semesters. This is just how it works. All right. So we have our R Thevenin. All that work for two values that we don't actually measure. But now we have the information we need. So now we go to our Thevenin equivalent circuit. It always will look like this. What's trippy is end of the week I'm going to teach you something. So another guy decided to take this theory and look at it differently. Because this is based off a current. Another guy came in and said, well, looking at voltage. One guy's like, I don't like dealing with voltage. I'm going to deal with it in current. This guy was named Norton. So Thevenin and Norton are the exact same thing. The only difference is one is based on current flows, the other one's based on voltages. Same theory behind them. I do too. All right, so we come back here. We had a 5.1K resistor. So we're going to put this guy back in there. 5.1 kilo ohms. This was R3. Our R Thevenin was 2.686K. And V Thevenin was 14.124 volts. So what would have happened if the voltage we had would have come out negative? How would we draw the circuit? Yeah, we would flip the battery, and we're measuring voltage from top to bottom, left to right, kind of keep that rule of thumb, same way we read. When we would get this value, it was going to give us a negative voltage because of how we're measuring with our meter. So we want to find voltage across R3. What do we use? Voltage divider. So 5.1 kiloohms divided by 5.1K plus the 2.686. We multiply that by our VThevenin, which is 14.124. Voltage across R3 is equal to, first off, ballpark, what should it be? About an eighth. Yeah, so you should have roughly 5/8, 3/4. Okay, so you should have 3/4 of this, so that would be 7, so about 10 volts. Just kind of a rough ballpark. It's going to be about 10 volts. So what is our actual value? 9.351? Yeah, like I said, ballpark. Just look at it and take a second and analyze it. What should this answer be about based on the ratios? And that's the cool thing with the resistors, is that these ratios will always hold true. So if you have more resistance on one side than the other, you're going to have more voltage across there. And then across the whole circuit, the more resistance you have, the less current you have.
So is that actually VR3?
That is VR3. This is 100% VR3. Now that we've solved that, we need to go back through and we need to solve for all the voltages of the circuit. With polarity like that. Can we do it? Yes, we can. Huh? Okay. It would take a couple of voltage loops to do this. Also, one of the things that we're going to be looking at is if we solve this center resistor using Thevenin, right now all we can get out of it is R3. Unless we use simultaneous equations, which is what we're going to talk about on Thursday or Friday. That's the math for this section. So the idea behind that is using simultaneous equations, we could determine what this is. And the way we would do that is we would do a couple of loops to go through these guys, and then we'd do another loop to get, like R4, where we have these values. We can run them through, we can plug them together, we can solve for all these voltages. Yeah. Yeah, we'd have two unknowns, so two equations. Yes. That's what we're getting. So that's what we're getting into next week. We're getting into mesh. And that's what this would be at this point, is we're combining multiple equations together to get one final answer. So in this case, we would not be able to solve this circuit just with the knowledge that we have. So that's why we're breaking this up into two different sections if you look on the quizzes. If you look, there's one that is the Thevenin bridge, find VR3, and then the other one is Thevenin bridge, find all voltages. So what we'll do is we'll do another one of these with you guys, get you guys familiar with these, and then we're going to switch gears into solving all voltages. We can use Thevenin to solve. This is to solve for all the voltages in the circuit. This is, yep. This is one of the limitations of Thevenin because it only gives us that value. Okay? But if we take out the right piece and we Thevenize to that one, we can then use that information to solve for everything. So, we'll go through another one of these, and then we'll show you guys how to use different resistors to Thevenize for it to solve for the entire circuit. Okay, go ahead and go to break. Does anybody want to hurt me yet? Oh, let me stop this.